Hello, and welcome to Quantum Computing. I'm your host, Donna Perkins, and our moderator today is David Ezell. Here's our agenda for the day. We have a few housekeeping things, and then we'll move right into our presenters. This webinar is being recorded and will be made available at Conexxus365.org. You can ask questions via the GoToWebinar interface. On the right-hand side of your screen, just click the little questions bar and type your question in there. Please do not ask any vendor-specific questions, but feel free to get your questions in early so we can prepare them for the speakers. Our webinars may be used toward PCI continuing education credits if the topic applies. Please contact 365 at Conexxus.org for information regarding a certificate for qualifying events. Conexxus does not endorse any products or services that may be described or mentioned in this presentation, and the views and opinions expressed in this presentation are solely those of the speakers and not of Conexxus. And of course, Conexxus is not providing any legal advice. Thank you to our 2022 Diamond sponsors. These organizations have been very helpful and supportive of Conexxus, and we're always grateful for their support. If you're not familiar with Conexxus, we are an independent, nonprofit, member-driven technology organization that sets technology standards for the convenience and fuel retail industry in data exchange, data security, mobile commerce, loyalty, point of sale back office, and more. We also provide vision by identifying emerging tech trends, and we advocate for our industry at a technical level with other organizations with a seat at the table when policies are being set to ensure that your organization is not adversely affected. And you can find us in several places. You can find us at Conexxus.org, at Conexxus365.org, and you can always find us on LinkedIn. Now I'd like to hand this over to our moderator, David Ezell of Conexxus.
Hello, everybody. I'm hoping that I'm appearing over here. I haven't done many moderators roles in this guise. So I want to introduce our two presenters today. We're really lucky to have them. The first is Steve Stevens, who is Executive Director of X9. I've known Steve for probably 20 years. X9 is an accreditation agency, and I believe Steve is going to talk about X9 in just a minute. So I won't go through too much of that. He is a graduate of the University of South Carolina with multiple degrees, including a master's degree in electrical and computer engineering. Phillip LaFrance is with ISARA, where he works on standards development in quantum cryptography with development organizations and industry groups across the globe. He is also working at, in addition to working at X9 in the Quantum Computing Risk Study Group, he is vice chair of the working group on quantum safe cryptography at the European Telecommunication Standards Institute. That was a lot of stuff to talk about. So we can move ahead, Donna. Before we go to Steve, actually, that's fine. So the first thing I wanted to say before I turn it over, these are really exciting developments going on, and we've had these guys come in to talk about them. Quantum computing, though, is really only one potential risk that we have in our security future. The concept of crypto agility, which Steve will talk about at the very end, is really a must for people to know about, and you should keep that in your mind the whole time we're going through this presentation. So with that, Steve, go ahead.
Great. Thanks, David. Give me 1 second here to get my presentation up. Okay, just double checking. You see it now?
Yep.
Great. Thank you, David, for the introduction. Again, my name is Steve Stevens. I'm the Executive Director of the Accredited Standards Committee X9. I'll tell you a little bit about that in just a second. But two things I wanted to do. First, I want to thank Conexxus. They have been a long-time member of X9. We have a number of people that participate within some of the different groups and standards bodies, and also in some of the management teams of X9. First, I'd like to thank Alan Thiemann, Gray Taylor, David, of course, you've been a longtime member, and help Linda Toth, and I thank Donna for helping us here with the presentation today. One other thing I want to point out on this particular slide, if you see the picture over on the right, that is a core of a quantum computer. That's an older IBM system that's been around now for a couple of years. I just want to point out a couple of quick things, and I'll refer to them later. If you look at the top tier here, you'll see what looks like pipes. And those are indeed, they're waveguides, and I'll get a little bit more into that. But I just want to show those to you so that when I reference them later on, you'll have seen them. And I'll show you this picture at the end. All right, let's get a little bit into the background of X9. This is what I call my shameless advertisement for X9. I can't get in front of a crowd without at least saying something about X9. We've been around about 40, actually a little over 40 years now. We're accredited by ANSI to develop standards for the financial services industry. We represent the United States on a number of ISO international committees. We actually run TC68. Some fun facts about 68 is that's the home of the ISO 20022 and the ISO 8583 messaging standards, which are the standard 8583 is which most of the credit card transactions are based on. So those are all maintained by 68. We are the manager of TC68, X9 is. We also represent the United States. We vote for the United States, and we do any other representation. So if you're interested in any of that, you might want to talk to us a little bit. We also are on TC 321, 322, having to do with electronic transactions and green types of accounting and finances for investments. We have approximately 100 member companies. We have over 200 representatives. We maintain approximately 130 ANSI standards and 120 international standards. We don't personally maintain all the internationals, but we work with all the other countries. There's approximately 29 what we call P member countries that work to maintain those standards. And then real quick, here's an org chart. We have actually 36 different groups within X9. I didn't want to put all 36 on here, but some of the key ones are our subcommittees. That's kind of the next level underneath our consensus body. The consensus body approves all the standards. X9A, real quick, basically everything to do with payments, apps for your cell phone, electronic payments, electronic benefit payments, anything to do with payments out of that group. Our B group has to do with financial services. They also do checks. Anything to do with checks, what's printed on a check, how they're processed. Also with back office operations having to do with legal orders and all kinds of fun stuff that banks and other financial institutions have to do with. Our C is our corporate banking. They get into how do corporations pay other corporations. One of the big issues or areas of influence right now is the remittance work. They're doing a lot of work with how to include remittance information in your payments to simplify the process. Our D group deals with stocks and bonds, and our F group deals with cryptographic types of work, also with X9. F6 group is our credit card group. So that's one of our biggest groups. They deal with PCI and the PINs. We are an integral part of that PINs. You see it down here. We actually have a seat at the table, and we have a voting. We vote on it. So we're the only outside group from the card brands that actually sits in and we vote on the actual internal standards. We have industry forums. These are open to the public. And the critical one here is the Quantum Computing Risk Study Group. This is the source of the information that you're going to be hearing today. I'm the chair of this group, and Phillip is our our editor and our supreme leader when it comes to physics. Even though I have an engineering background, he has a lot more background in physics than I do. So when you see him rolling his eyes over there, that means that I made an analogy that's kind of close, but not quite. And he'll have some words for me after the presentation. So Phillip is going to be my color commentator. When he's not rolling his eyes for some of the stuff I'm saying, he'll be providing some good insight into what's going on. Okay, that's enough about us. Now let's get down to what you're here for. What is a quantum computer? Real quick, this is a kind of a high-level definition of a quantum computer, but one of the things you need to remember ahead of time is hopefully some of you had at least a little bit of physics, either in college or high school. And you remember there's several kinds of physics. You have astrophysics, which deal with large bodies, stars, planets, things like that. And then you have what's called quantum physics. And quantum physics deal with what happens at the very, very, very small particle level. And there are really weird things go on at that level. And because we can't see them with the naked eye, we don't understand sometimes how they work, why they work, that they even exist. And that's why quantums are kind of hard to understand, because a lot of the stuff they do, you just can't see. So what's the definition? A quantum computer harnesses discrete physical particles that exhibit quantum mechanical properties to create the actual computational elements that will be used to do normal additions, subtractions, all the normal stuff a computer can do. They will actually harness these particles, and they'll look at the capability of these particles to perform these functions. So what are some of these particles? Well, you have electrons. These are your old friendly electrons that are in orbit around atoms. We actually have the ability to track an electron and follow what it's doing. Protons of light make up light waves. They will exhibit quantum properties. Ions, almost any particle that exhibits quantum behavior could be harnessed. However, we don't have the capabilities to harness every particle that could be used. We do have the capability to harness some of them, and that's what we're at the moment. We have to use those particles. All right. Next, now that you know what a quantum is, why should I care? I like my little picture here. I hope you're not the girl on the right that's already gone to sleep. One reason you should care is RSA cryptography. It's commonly used on the internet. It's a class of cryptography that is called a asymmetric type of algorithm. It's sometimes called public-private key. You have two keys. One key is used for encryption, one's used for decryption. And just about everything on the web takes advantage of this. Anytime you see a secure web page, it's more than highly likely that the underlying structure or the underlying algorithm is something either RSA or something based on RSA. Just for examples, if you take a RSA algorithm and you take a 248-bit long key, there's approximately 10 to the 615th power unique bit strings to go along with that key. That number is perfectly meaningless to the average person listening to this because it's just too astronomical. Just think of a 1 with 615 zeros after it. For comparison, if you take every atom in the known universe, every atom that makes up the Earth, all the planets, the sun, every solar system, the millions of solar systems that exist in the galaxy, and the billions of galaxies that exist in the universe, all those atoms is 10 to the 80th. That's a significantly larger number. So what that should mean is it takes a lot to break that code. How much does it take? Well, a classical computer, the best we have today, is estimated to take 6 quadrillion years to break the code. Now, people have different estimates. You can use different algorithms. What's the takeaway here? It's a long time. You think of quadrillion, you have thousands, millions, billions, trillions, quadrillions. So it's a long time. Even if we're off by a factor of 100, it's still a very, very long time. All right. Now, why should you worry? Why should you care? It's estimated that a large, stable quantum computer would only take minutes or seconds to break the code. Now, I emphasize large and stable. Those do not exist today. We do have quantum computers today, but they are not large and they are not stable. But they are working, everybody's working to get large, stable quantum computers. And we'll get into that a little bit more in a few minutes.
Yeah, and if Steve, if you don't mind me interjecting. Sure. As the technology evolves, different quantum computers of different sizes are going to be able to do different things. But just to sort of put the idea in the audience's head for now, a quantum computer that is large and stable enough to actually threaten the cryptography that we use today, this is what we refer to as a cryptographically relevant quantum computer. So a computer that can break RSA 2048, so that's factoring 2048-bit RSA moduli, we would call that a cryptographically relevant quantum computer. So just something to keep in your mind, and I think Steve's going to point that out later on in this presentation.
Yeah, we'll talk about it. Right now, everything we have is irrelevant, but they're working on it.
And Steve,
right. Yes.
I had a couple of things before we jump into this next session. I wanted to be sure that people know to be prepared for a deep dive. This is a very, very technically interesting, fascinating, dense section. Richard Feynman, the guy who invented or really came up with the best examples of how quantum computers might be used, once said he thinks he can safely say that nobody really understands quantum mechanics. Now, if that guy said that, then you can feel okay about having to rely on the analogies that we're going to show you, because that's really all they are. So, Steve, take it away.
Yeah, if you don't understand a lot of this stuff, you're in great company. All right. What makes a quantum computer so different? Are they really better than a classical computer? And we'll get into some things. I hate to bust your bubble on some of this, but quantums are not real good at a lot of stuff. But we'll talk about that in a minute. Let's talk a little bit about how they work. We call this the red ball problem. And if you look closely at Philip, you'll see his first eye roll. Pretend that somebody gave you 10,000 golf balls and they put them on the floor of a big gym or someplace, and they took one golf ball, they painted it red, and they made it a very textured, rough finish. They blindfolded the person and said, please go find the red ball. Well, you start by picking up each ball and you go through a serial process. Is this it? Is this it? Is this it? Statistically speaking, you're going to have to pick up half the balls before you find the red ball. If you've got really bad luck, you might have to, it might be the last ball you pick up. So you'd have to go through and pick up every ball, but at least half of them statistically. Well, that's okay for maybe 10,000. What if you had 10 billion balls? That's going to take a while. Now you kind of get a feel for some of the cryptographic issues and the breaking of it. So how does a quantum work? Well, a quantum, take off the blindfold and find the red ball. Well, that's easy. You just look out there, you find the red ball, and you pick it up. How many balls you pick up? One. Now, I don't mean to try to tell you that a quantum can see, but remember I told you earlier, quantums take advantage of quantum physics and certain types of properties that we as humans can't see. We don't experience on a daily or even ever probably we don't really know when they're there. So there's things going on outside of our normal vision that we don't contemplate are actually there. And it's using these capabilities that are totally alien to our normal world. They can, in essence, see the red ball and pick it up. Now, they use totally different techniques. The other thing they do, everything is probabilistic when it comes to quantums. There's no guarantees. If I tell somebody to go pick up every ball, eventually they're going to find the rough ball. With a quantum computer, you're dealing with electrons. If you remember, they're waves in orbit around an atom, and everything is probabilistic. You don't know if it's here, there, wherever it is, and the gates that you run things through, you still end up with a probabilistic. Now, what that really means in practice is if you run a program on a quantum, the first answer may not be the right answer. The second answer may not be the right, but probably the fourth or fifth one is guaranteed to, if you get enough samples, you'll find the answer. And it's far less than the quadrillions of answers that you might have for the other one. And that's what makes it so attractive to use. All right, let's go just a hair farther. I hate to go too deep into this, but conventional computers, if you're familiar with, they're ones and zeros. They're based on human concepts. They're rules that humans define, like 2 + 3 = 5. They operate in a serial process, like picking up each ball and checking it. They're basically based on the Turing machine that came out, I believe that was in the 30s or 40s that Turing came up with that. And they're arbitrary representations of ones and zeros. It's typically based on either current or voltage, depending on what type of logic you're actually using. Again, quantums are harnessing quantum phenomena that's inherent in matter. You're actually tracking an electron, and you're using the electron to do your math for you and to look at the polarization, say, of a photon. Totally different concepts. There's two main properties that a quantum will have that just blow people's mind. They're totally alien to what you're used to today. One's called superposition. The other one's called entanglement. We'll get into both of those very briefly, but just remember those names. If you get anywhere close to a quantum, you'll hear them. All right. Next is just a visual representation. I'm not going to spend any time really on this. A classical computer, you have 1 or 0, nothing in between. A qubit, you have a 1 or 0, but you see this sphere here. This is called a block sphere. A qubit can represent, when it's in superposition, any point on the sphere. And programs in a quantum computer, you start with a 1 or 0 in your qubit. You immediately put them into superposition, which means they can range anywhere through here. And what really gets people a little spooky, along with one of the other things in a minute, is the fact that you can have all of these basically at the same time. So there's a lot of things to digest here.
And Steve, maybe I can just add on to that quickly. Mm-hmm. I think it's helpful to think about quantum superposition in terms of parts of a whole. So if we think about a classical bit, it's either a 0 or it's a 1. There's no in between. There's no other options. That's the dichotomy. Whereas a quantum bit in superposition, so a qubit in superposition, you can sort of think of it as being part 0 and part 1. Where actually the size of those parts are not necessarily equal, and they actually correspond in some sense to the probability of that being the answer you get out when you measure the system, which is probably something that's a little bit too in the weeds for this conversation. But I think thinking about it in that way is really useful, especially for people who maybe don't have the math background or haven't seen this stuff before. A qubit in superposition, you can think of it as being part 0 and part 1. And in my experience, that's been helpful. And if it isn't, I'm sure they'll let us know in the Q&A.
Thanks. I wasn't going to go over this slide, but if you look at this is a little bit more detailed picture of the sphere, and you see a point on the sphere, and you notice that if this is the value of the qubit, you look at the angle here, and there's a percentage. It's going to be some percentage of 0, some percentage of 1. And as it goes around, the percentages change. So the math is unbelievably bad. So I'm not even going to get into that. But all right, here's another example. And those that are counting eye rolls, you might want to get your counter ready. This has to do with the coin flipping analogy. And one way to think of a qubit is take a coin and flip it up in the air and have a strobe light. As the coin, let's say you start with a 1, and you just assign arbitrarily, say heads is a 1, tails is a 0. You flip it up in the air and you get a strobe light and you hit it. As it flips through the air, when the strobe goes off, you're liable to see the coin in various different positions. It might be vertical, it might be horizontal, might be an angle 45 degrees, somewhere in between. But what it's doing is it's rotating through all possible combinations of 1s and 0s as it's flying through the air. That's one characteristic of a qubit when it's in superposition. Another one that's totally alien to the conventional world is phase. Let's assume there's a date on the coin, and that date is facing the person when they are holding it. And then as they flip it and as it rotates through the air, it not only flips over and over, the coin actually rotates a little bit. And when it lands, let's say it lands heads, but the date is now rotated 90 degrees. That's the phase of it. And the reason that's important is there are programming gates and that you can use in a quantum that take it some advantage of that particular capability to try to reach the answer you're looking for. All right. And these are just it's a summary. These are some of the, qubit and superposition. These are just some of the things that they can do. And a quantum or a classical bit can only be a 1 or a 0. If it's in between a 1 or a 0, having designed many computers in my life, that's called an error, and it will shut down. Whereas a quantum computer lives its life during operation in between a 1 and a 0. All right, real quick, I don't want to get too far in the weeds here, but people that are familiar with programming classical computers, you have logic gates, and or nor, those kinds of things. If you have an AND gate, if both inputs are 1, you'll get a 1 out, which is high voltage. Otherwise, you'll get a 0. I'm not going to go back through that. Quantum programs also have programming elements, and they're called quantum logic gates. And they work somewhat similar, but let me give you some examples. There are a couple of the gates that you can have. One's called a polyx, and Hadamard, I believe I say that right, is another one. These are gates that you run a qubit through, and polyx is a NOT gate. If it's a 0, it becomes a 1. If it's a 1, it becomes a 0. And some people have found that since you have no background in quantums, what I try to do is give you at least a small, a little idea about how they work. People always wonder, well, how do you actually do that to a quantum? If it's an electron in orbit around an atom, well, the simple answer is you hit it with electromagnetic radiation. A very short pulse at a certain frequency and amplitude will cause the electron to change its orbit slightly. And it'll go from a 0 to 1 or 1 to 0. And people ask, well, how do you hit it with electromagnetic energy? It's called a microwave, just like you have in your kitchen, except these are very precisely controlled microwaves. And by varying the frequency, the amplitude, and the duration, you can create almost all of the gates that are used for programming a quantum computer. So just think of it as a really high-end microwave oven. One other thing to point out, that microwave, just like in your kitchen, is controlled by a microprocessor. And a quantum, and guess what? They're also controlled by conventional computers. So a quantum cannot exist without a conventional computer actually operating it. And one of the parameters of a quantum is how fast these gates operate, which gets back to the hardware and the controller for how fast they can pump the radiation in and perform the different gating functions. All right, that's up for superposition. Now we're moving on to another fun fact. This is called entanglement. And if you see the picture of Albert Einstein, he actually came up with the initial thought process or the postulation that quantums might exist in some of their weird capabilities. He came up with entanglement. He called it spooky action at a distance. He never fully believed that it existed. He died not having, there was no experimentation that was successful at the time. He still did not 100% believe that it was possible because on the surface, it tends to violate some of the normal rules and laws of physics. The definition, this is really kind of in the weeds a little bit. Let's just simplify it by saying if you have two qubits and they're entangled, one will mirror the other one. In other words, if you operate on one of the qubits, a similar type of operation will occur on the other qubit. That's why it's called spooky. The two qubits can be separated by a distance, sometimes a large distance, miles, kilometers. There's been a number of types of operations, testing that's been done on this. And there is almost an endless speculation as to how they work. They've used every kind of sensory they can think of to listen in on the two qubits talking to each other. And everything we use, the qubits are silent. So we don't exactly understand how they do it. We know they do it. We will eventually figure out how they do it. But if you're a Star Trek fan, there are people speculating that there's subspace communications going on. You have all kinds of other potential properties that we don't fully understand that take place, all of them in an attempt to say there's a easy to explain operation going on here, but we really don't. Philip, you got any color to add? I know this gets into the highly speculative area, but it's also some fun stuff.
Well, similar to what you were saying before, don't feel bad if you don't walk away from this with your head perfectly wrapped around what entanglement is. But yeah, really what it is it is physically correlating the properties of two different particles. So maybe I have an electron over here. It's in superposition of spin up and spin down state, as we say. If I can just describe that on its own, then it's not entangled. But if it's entangled with another electron that's also in a superposition of spin up or spin down, and if I can't actually describe the state of one of the electrons without including some information about the other one, well, then they're entangled. So their physical properties actually become correlated. And it doesn't matter if they're separated by nanometers or by galactic scales, the physical properties of these things are correlated so that if you measure one, whatever that means, you automatically measure the other one. It's absolutely just bananas, and it is some of the most fascinating, interesting stuff out there.
And it tends, on the surface, it tends to violate the maximum speed law in the galaxy, the speed of light. So if you want to do some mind-boggling types of reading, this is a good one to start with. All right. Let's talk a little bit about the power of a quantum computer. If you have a conventional computer, you want to double the power, you double the number of bits. If you have a 32-bit machine, you want to double the power, you go to a 64-bit machine. Now, there's some overhead in there, so it's not an exact doubling, but it's close. The other thing to point out is in a conventional computer, the bits are just memory elements. They're just storage of a 1 or 0. Now, if you want to double the power of a quantum computer, you add a single qubit. Because a qubit in a quantum computer is both a memory element and a computing element. So if you have a 50-qubit machine and you add 1 qubit to it, so it's 51 qubits, you've doubled its power. And today we have a 127 qubit machine, so that would be 72 to the 77th power more powerful than a 50 qubit machine. It's estimated that when we got to the 50 qubit threshold of quantum computing, that computer equaled the power of the largest conventional computer in existence today. And like I say, we have one today that's 127 qubits. So we're 2 to the 77th power more powerful than the largest, most or conventional computer that we have today.
Yeah, and Steve, let's go back to what I was just talking about parts. So superposition being in parts, right? If I have, again, just a single qubit, it can be part 0 and part 1, right? But if I add another qubit to that system and I entangle these things together, then that entangled system can represent part 00, part 01, part 10, and part 11. So that's all the possibilities for a length 2 binary string. So in that sense, an entangled system is operating on all of the possibilities at the same time. In popular articles, you might hear something like a quantum computer looks through all possibilities at once. That's not exactly true, but what's true is that there's a quantum object that is in some sense part all of the possibilities, and these are the things we work with. So if I add another qubit onto this 2-qubit system, Now this thing can represent in part 000, 001, all the way down to 111. So I go from 4 possibilities all the way to 8 possibilities. So adding that one more qubit really doubles our compute power. And this is really one of the most fascinating things about quantum computing, and it's what makes them, in theory, so useful, so powerful.
And think about quantum computers that will have one day that have like 10, 20,000 qubits. The computing power is just, it's almost like that number 10 to the 615th power. All right, let's talk a little bit about what quantum computers are good at. Again, I like to say, I hate to bust your bubble. You'll hear stuff on the radio and TV. Oh, quantums are going to be they're going to be Skynet. They're going to take over the world. They're going to do unbelievable things. They're going to eavesdrop on all your data. They're just, I mean, I've heard all kinds of fanciful type things that they're going to be able to do. But believe it or not, they're not good at most things. But so what are they good at? Well, they're good at prime number factorization, large number prime number factorization. And that would be needed for breaking security, such as with RSA. They're good at forecasting weather or doing weather modeling. At least we believe they are. Remember, we don't have computers big enough today to actually do it, but we have a lot of theoretical models, a lot of simulations. So this is what we believe they'll do. They're good with chemical interactions. The drug companies are just really anticipating the first really big quantums, because they'll be able to test drug interactions to see if it's going to work the way they think it would. All the stuff you hear about trials where we went through the vaccine trials where they did human testing, they'll be able to do a lot of that automatically with a quantum, and they'll know almost to a very high degree whether or not it's going to work before they ever put it into a human. Calculating discrete logarithms used in breaking elliptic curve type cryptography is another one of the type systems we use. And some believe they will be good at determining complex patterns in data.
Yeah, and I think this is an important thing to emphasize, right? Obviously, our bias is in information security, privacy, and cryptography. And we really want to get across the idea that quantum computers can break the cryptography that we use today. So elliptic curve cryptography and RSA. But not everything that a quantum computer can do is going to be harmful or damaging. In fact, many of the things that we expect quantum computers to do will actually be immensely helpful to humanity. So Steve's mentioned some things like better weather predicting, as far as like chemical interactions, maybe even bespoke pharmaceuticals, maybe based on your own genomic data, designing better materials for better superconductivity and less energy loss during transmission, designing better fertilizers to reduce greenhouse gas emissions, and any sort of optimization problems. So plenty of applications in finance, stock market, and things like that. They're not good at everything, like Steve said, but the things they are good at are many, and we're really looking forward to getting these out there in the wild.
Yes, thanks. Some other fun facts about a quantum computer. They're expensive to operate and build. Now, I read one report where one of the computers, they estimated it was $1 billion. Now, that included the development cost. A lot of scientific research went into that, but still, they're not cheap. And a lot of them cost as much as $100,000 per hour to operate. And believe it or not, when you hit the start button, there really isn't a start button. But when you start the sequence to bring it up, you can wait as much as 34 hours before it's ready to operate. Why? Well, most of the quantums today, and this is something that's being actively worked on to try to give them a little more leeway, but they need to operate at extremely cold temperatures. If you remember some of your temperature scales, Kelvin, 0 Kelvin is absolute zero. That means there's no energy, there's no thermal energy. The atoms are pretty much frozen in their lattices. Electrons are still orbiting, but the atoms are pretty much frozen. There's little or hopefully no vibration, and A quantum needs to operate at 3 millikelvins, somewhere between 0 and 3 millikelvins. If you want to compare that to something, if you went out to interstellar space, light years outside of our solar system, in the deepest, darkest areas in deep space, there's a temperature, and they believe it's to be somewhere around 2,400 millikelvin. That's 800 times warmer than the operational envelope of a quantum computer. So when a quantum is operating, it's not an exaggeration to say it's probably the coldest of the area inside of that is colder than any other place in the universe. One other thing about quantum computers is they have something called coherence, and they only maintain it for milliseconds. Coherence, remember, we're looking at electrons in orbit, and anything that changes the orbit or the parameters of that electron, such as the spin, that is not the direct result of a programming element causing it to change, changes the fidelity of that qubit. It's no longer representing what you think it should represent. The noise of the system is now coming into play, and your qubits are beginning to not do what you expect them to do. And what we need are quantums that have a coherence measured in hours, but right now they're measured in milliseconds, which means they're only good for those milliseconds. Past that, the data becomes corrupted, and I'll say it's meaningless, but it's close to it. The largest quantum computer we have today, 127 qubits, and IBM came out last year. We're expecting another one from IBM anytime now that'll be in the 430 qubit range. So that's going to be a pretty massive increase when you think of the difference in the number of qubits. That raised to the second power, or the second power raised to that number. Again, they're only good for milliseconds. What's the culprit? Heat. Remember, we talked about how do you change the parameter of an electron? Well, you hit it with electromagnetic radiation. In this case, microwaves. Well, what do you do when you put a glass of water in a microwave? You heat it up. So the actual mechanism by which you implement a program in a quantum is actually causing heat, and that causes to lose coherence. Now, what we need is a refrigeration system capable of rejecting that heat as it's being introduced, or we need qubits that can exist in a more noisy environment at a little higher temperature. Either one works, and I think people are working on both. To break a 256-bit, 248-bit RSA code in a reasonable amount of time, we believe it'll take between 10 and 50,000 physical qubits. And the reason we need that many is because we need to create a logical qubit, and I'll talk about that in a second. Here's the takeaway from this. At the moment, none of the technologies that we're using today are capable of reaching this requirement. We do have computers, they do run, they're pretty good sized quantums, but they're not stable, and the technology that we're using on them today are not going to get us there. But it's a stepping stone. By looking at what we have today, we understand the shortcomings, we understand what needs to be improved upon, and trust me, there are thousands upon thousands of people and tens of billions of dollars being put into this new technology. So we don't know what it is, but we know that there are a lot of people working on it. Now, out of the depths of the hardware side, let's talk a little bit about some of the algorithms and some of the things we need to be doing. We tend to refer to the algorithms that will be around after a quantum becomes cryptographically relevant as post-quantum cryptography or cryptographic algorithms. These are algorithms that are either safe or highly resistive to attack by a quantum computer. NIST, a government agency that's responsible for standards, has been working to vet quantum safe cryptography since 2018. They've had several rounds. Right now they're finishing up round 3. We were actually expecting the results in December. We were just recently informed by Dustin Moody, who works with X9. He's a member, he works for NIST, but he helps out with X9, that they were going to be delayed a little bit. And so we don't exactly know when that will come out, but it won't be too much longer. A little bit about two different classifications of cryptographic algorithms. We have asymmetric algorithms, and those are things like we said earlier, those are like public-private keys. RSA is a member of that. Most asymmetric algorithms that are in use today will be compromised by large-scale stable quantum computers. It's just a fact you're going to have to get used to, that the data will be compromised. Now, on the symmetric side, which is you have a single key, those are like your military grade hardened systems. One of the key ones today is AES. It's generally safe. Quantum may have a small advantage, but by increasing the key lengths, you can overcome that. But here's the issue. Most of your symmetric or the AES, when it's in use, you share the key using an asymmetric algorithm like RSA. So if you break the RSA front end to it and you find out what the key is, you don't have to break the symmetric algorithm because you already have the key. So it's really critical that the asymmetric portions of the cryptographic systems, we have to harden these systems or we're going to be in trouble. Now, one of the things is X9, we maintain over 100 financial standards. A lot of those have something to do with cryptography or protection of data. And as soon as NIST comes out with their list of vetted algorithms, then we're going to start work on updating our standards, and those standards will flow to the vendors for the software vendors, and it'll then go out to the users that need these new algorithms. And to talk a little bit about this, I have this little diagram that I thought of. If you think about all the cryptographic algorithms that exist, here's the ones within this little green circle here that are easy for a quantum computer to break. And then you have in this one, these are the algorithms that are hard for a conventional computer to break. Well, there's a subset that are in both. They're easy for quantum, hard for a conventional computer. That describes your RSA algorithm. It falls neatly into this little space, as do a lot of others. And then there's one more. This is the hard for a quantum computer to break. And everything that falls in between here, hard for conventional, hard for a quantum, those are your post-quantum candidates for cryptography. Those are the ones we're looking for now. Now, 40 years ago, when RSA came out, there could have been other options. Had we picked one from this area instead of from this area, we probably would not be having this conversation right now, because your cryptographic products and stuff would not be susceptible. But unfortunately for us, it came out of this area. So now we have to solve this problem again. All right, here's the one everybody loves to talk about. When should we worry? All right, we have one of the members of our group is Dr. Michaela Moscott of the University of Waterloo, which is actually up where Phillip is. And he came up with this formula. He's the first person that I saw that put it out. And we call it the worry formula. It's very simple. X plus Y, if it's greater than Z, then it's time to worry. All right, what is X? X is the time it takes you to migrate to the new quantum safe cryptography. If it's 5 years, it's 5 years. If it's 6 months, it's whatever it is. All right, why? What's the lifespan of your encrypted data? In other words, how long do you want your data to be secret? Put another way is, when would you be okay if your encrypted data was suddenly put out on the internet in the clear so everybody could see it? If that's 10 years, it's 10 years. If it's 100 years, it's whatever it is. So you take those two numbers, you add them up, and then the third one is the arrival time of the threat, which in this case is a large scale, stable computer, or what we've been referring to as a cryptographically relevant quantum computer. When are those going to be available? I'll give you an example here. If your migration time is 6 years, your lifespan's 10 years. If the arrival time of a large scale stable quantum computer is 15 years, guess what? it's time to worry, because you are already past the time where you need to get your data encrypted. You say, well, why? It's only 6 years. Yes, but almost everything on the internet is being recorded today. So right up to the end of your 6 years, there is a good chance some of your traffic is, or all of it in some cases, is being recorded. And if you want that data to be secret for at least 10 years, 9 years out, the quantum's going to be here. They're going to start decrypting some of that information that was stored. And there's a chance they could get access to your data, and it would no longer be secret. So you have to put in these numbers. They're different for every company. And the hard one is this threat. Just at a meeting of the quantum group just recently, I think Philip actually brought up that there was a group of engineers and people researching quantum computers. They now think it's only 8 years out. But there's other groups that think 15 years. You see some as much as 20 years out. You kind of have to know a little bit and try to look at some of the people you trust and say, what are they saying? And one of the things we put in our paper that we produce and keep on our website is some analysis of that. We need to go back and look at that 8-year one and see what's actually in there. But this is your worry formula. Now, to the cryptographically relevant quantum computer, what is that? That's a computer that has error correction and fault tolerant qubits, or logical qubits. It'll take some number of physical qubits to create a logical qubit. We've never done it, so we don't know exactly how many. It could be 10, could be 50. It's all over the map. But we think we need at least 2,000 logical qubits to be a relevant, cryptographically relevant quantum. Today, we're at 127, and we know that the technology to build this computer will not get us to this level. The coherence or the stability needs to be measured in hours, not in milliseconds. And the quantum gates that are used as your program in a quantum, they need to be high speed and they need to have precision. So one of the things, it'd be nice if they didn't cost $1 billion. We need them to be cheap and cheaper to operate, cheaper to build, which will increase the number that are out there. How do you prepare? For the asymmetric cryptography, RSA and other algorithms will not survive an attack by large-scale stable quantum computer. This type of cryptography used by web browsers and widespread use in the engineering has to be changed. The symmetric algorithms, AES, we use an algorithm called Grover's algorithm to attack them. Maybe we'll have to increase the key length. There's still a lot of work being done to determine exactly what needs to be done. We believe that the AES algorithm will survive. And maybe the worst case is just change the key length. All right, steps to take. We're almost done here. Identify the data that you use that's at risk. All those asymmetric algorithms. Identify the systems that process the data and the vendors that provide those systems and any support that is needed for that. Keep an inventory or make an inventory of all these so you know what you have to worry about. Ask the vendors to disclose their plans and time schedule to migrate to post-quantum cryptography. Ask them if they're coordinating their work with the work of NIST or standards bodies like X9. They need to be working with one or both. Ask about, do they have a architecture that would encompass what's called crypto agility? If you don't believe, or if you believe this is the last time your algorithms are ever going to be at risk, or that you're ever going to have to change an algorithm, then you don't have to worry about crypto agility. But if you think there's a chance that in the future you might have to go through this exercise again, then talk to the people about crypto agility. What this allows typically is more than one algorithm to be used at one time and to determine which algorithm they should be using. And it's a way to reduce future pain. In the networking world, back in the early days, we had every kind of protocol you can imagine. We had XNS, we had TCP/IP, we had Token Ring from IBM. Yeah, we were able to exist because we had a network architecture that allowed those to exist side by side and everything still worked. All right, next, create a plan and a timeline to migrate your systems and data to the post-quantum cryptography. No, hopefully you won't have to actually get down in the weeds and do the programming, but you may, it just depends. But talk to your vendors, make sure you know their plan, and make sure that you rerun the worry formula often so that you can adjust your plan as necessary. If something gets pushed out, redo your worry formula. If something gets pulled in, or the data, the time you need the data to be secret, or the expected arrival of a quantum changes, then you need to go out and rerun your formula. So lastly, just some quick milestones. NIST is vetting all of the quantum safe algorithms. We expect to have that information shortly. They had one problem they had an algorithm called the rainbow algorithm, and they were spending most of their time trying to make sure that a quantum couldn't break it. What they forgot to do is check to see if a conventional computer could break it. And IBM published a report just a couple of weeks ago that with your laptop computer and a spare weekend, you could break the rainbow algorithm. So it turned out to be really difficult for a quantum, actually pretty easy for a conventional. So that's been taken off the list. In the past, one little point, NIST has recommended kind of single algorithms like AES. This time around, they're going to recommend a suite of algorithms, and we're going to have to pick which one to use for different things. You could use one algorithm for credit card data, one for banking, faster payments. Each one of these algorithms is going to have a different processing requirement. Some of them may be processor intensive to the point where they're not going to work on a card reader terminal. Yeah, so you're going to have to take a look at where they're going to be used, what type of hardware is going to be available, and you may have to pick the ones that's best for your environment. And you may pick different ones depending on how you're going to use them. And then lastly, kind of all browsers and web servers are going to have to be updated. That's just a given. All right, last slide. Here's that picture of the quantum computer, the core. If you look closely, you can kind of see the wave, the little copper tubes in there. I think these are gold plated, but you can see the microwaves, and these tubes are all throughout it. So that's my presentation. Philip, you have any wrap up comments?
No, just say that thank you, Conexxus 365, for having us, and I really look forward to the question and answer period following this.
Great. Well, I'll turn it over to David, and thank everybody.
And yes, thanks again, Steve and Philip, especially for the color commentary. And during Q&A, there will be extra credit for anybody who can tell us where the idea of the quantum came up first. So thank you very much. Hello, everybody, and thank you for sticking with us. We're almost at the end of our hour, but I think we have just a minute or two that we can forward some questions. I think you sort of answered this, either Steve or Philip, but it's what are the projections for when quantum computers will be practical for use? I think they're, a more concrete answer. And the other one, this one is something you didn't talk about. What technology is used to cool these systems?
Yeah, I'm happy to take this one. And thank you very much, Steve, for that presentation. So the projections vary, and I think one of the important things to keep in mind is different sizes of quantum computers are needed for different things. So I mentioned that there are all these wonderful applications we have in mind for quantum computing down the line, and those actually might require smaller computers. The cryptographically relevant quantum computers tend to be a little bit on the larger side. But the best estimates right now, and I would refer the audience to the Quantum Threat Timeline report by Dr. Michele Mosca. I think that was through the Global Risk Institute. They have this really nice probabilistic breakdown based on the survey that they did. And the current estimates are something like low single probabilities in the next 5 years to get a cryptographically relevant quantum computer. Maybe you get low double digits in the, say, 7 to 12 plus or minus year period, and then it just gets higher and higher. By the time we get out to the 20-year period, the probabilities are pretty high into the double digits. And as a personal feeling, I think that this is actually an underestimate, but that's a whole other conversation. So I think we're going to have cryptographically relevant computers here before you know it. And regarding the cooling question, which is a really, really good question, One thing to note is not all qubit architectures need supercooling, right? So we're still working on technologies that maybe can run a little bit hotter. But for some of the systems that actually the IBM system that Steve showed, I think this uses a liquid helium-based system. I forget the term off the top of my head.
Well, there's usually at least 3 or 4 separate systems. Initially, they'll use liquid helium to get you down to the lowest point using conventional methods. And then I've seen systems that use everything from lasers to try to fix atoms in space to radioactive isotopes and certain characteristics of their ability to cool. The thing is, they're very expensive. There's a limit to how much heat they can reject. And the problem is being attacked from several directions. One is trying to get qubits that will operate at a hotter temperature, like you said, and the other one is trying to get cooling systems that have a higher ability to reject heat. Either approach or both will help.
Yep. Well, we're out of time, folks. I'm really sorry about that. You can contact Steve. You can contact me. Steve put his contact information up there, but Philip is available to answer questions too. Actually anxious. You may want to ask Philip what he does for a living, because he is a guy who is actually making a living in a real life company writing software addressing these problems. So this isn't just fake news. This is actually people who have companies who are working on all of this. Thank you for joining Conexxus 365, Steve and Philip. Again, thank you for your expertise, your knowledge. Thank you, everybody, for coming in. And we will hopefully see you all at the annual conference. Thank you.
Thank you very much, everybody.
Thanks.